다음 세션에서는 나사의 전인수 박사님이 아르테미스 시대의 심우주 임무를 위한 우주 방사선 과제 달에서 화성까지를 주제로 발표합니다. 전인수 박사님은 1991년 UCLA에서 원자력 공학 박사학위, 응용 플라즈마 물리학 및 핵융합 기술 분야를 취득했습니다. 학계와 산업계에서 9년간 근무한 후 2000년에 JPL의 미션 환경 그룹의 선임 기술 직원으로 입사했습니다. 2004년부터 2011년까지 그리고 2014년부터 2020년까지 자연우주 환경 그룹 책임자로 근무했습니다. 현재 JPL 우주 방사선 센터의 책임자이자 나사 기관 전체의 우주 환경 기술 분야 팀 TDT의 수석 기술자 및 부기술 펠로우를 겸직하고 있습니다. 그의 주요 전문 분야는 우주 방사선 환경과 우주 시스템 및 행성에 미치는 영향입니다. 현재 핵 행성 과학 및 우주 물리학에 대한 연구를 수행하여 우주 방사선과 관련된 많은 나사의 지원 프로젝트를 이끌고 있습니다. 또한 MSL, 유로파, 푸시케, 임무 및 아르테미스 게이트웨이, 헤르메스의 과학팀원으로 활동하고 있습니다. 오늘 발표에서 전인수 박사님은 현재와 미래의 우주 임무에 대한 우주 방사선의 도전 과제에 대해 논의할 예정입니다. 전인수 박사님은 전자기 방사선, 저에너지 및 고에너지 입자 방사선, 중성 입자, 미세 융성체, 궤도 파평 등 우주 임무가 노출되는 혹독한 환경에 대한 개요를 제공할 예정입니다. 박사님은 우주 환경에 대한 이해와 임무, 성공을 위한 승무원 및 우주선 시스템 보호의 중요성을 강조할 예정입니다. 박사님은 우주 방사선 환경에 대한 최신 지식을 발표하고 이해의 격차를 파악하며 우주 방사선에 대한 미래 연구에 대해 토론을 장려할 예정입니다. 박사님을 환영해 주세요.
Yeah, hi. My name is Insoo Jun from NASA Jet Propulsion Laboratory, JPL. First of all, I'd like to thank the organizer of the conference for the invitation. It's my honor and pleasure to be able to make a presentation to this special audience. Today, I'm going to present a very short introduction, overview of space radiation challenges for deep space missions in the Artemis era, from the moon to Mars. So these are the topics that I will cover today. First, objective of the talk, and then I will provide a really short overview of the radiation effect, especially related to single event effect. And then I will provide overview of the space radiation environment, mainly solar particles, galactic cosmic rays, and the environment on the surface of the moon and Mars, since they are all most relevant with the single event effect, and my own personal take on gaps in the future. And I will conclude with a summary of the presentation. So the objective of my talk is very simple and straightforward. Planning is underway at NASA for returning humans to the moon since the Apollo era, and later to Mars. And many robotic deep space missions are also being envisioned by many countries around the world. For all those missions, the space radiation has been and will be a key consideration for the mission success. So this talk attempts to summarize my personal view on the state-of-the-art knowledge on the space environment relevant to Artemis and the single event effect, and also try to provide the impetus for further discussion on the future need. So here's the notional, very ambitious mission scenario for the Artemis program, spreading over many years. We already saw the successful Artemis 1 mission in November 22, when we sent the human-rated spacecraft to the moon using the powerful Space Launch System, SLS, the first in the 21st century. The second Artemis mission is planned for November 2024, next year, when the humans will be actual humans will be orbiting the moon for the first time in the 21st century. It will be followed by the series of the missions, including Gateway, Deep Space Crew missions, and Human Landing System, HLS. And these missions will be accompanied by other missions, such as multiple CLIPS missions, commercial lunar payload service missions, and the Viper, a volatile investigating polar exploration rover, etc. And eventually, human will be venturing into Mars in the distant future. So, as for the space radiation environment, as many of you already know, generally speaking, there are three types of natural space radiation environment. Particle from the sun, ever-progening low-energy solar wind, and sporadic solar energetic particles from solar flares and coronal mass ejections, and highly energetic galactic cosmic rays, and trapped particles found in planet and with the intrinsic magnetic field, for example, Earth. Actually, and for missions to the surface of the planetary bodies, for example, to the moon or to Mars, this surface radiation environment should be considered, including albedo neutrons. And finally, although I'm not going to cover today, for missions with the nuclear reactor, special radiation from onboard nuclear reactor, that is neutrons and gammas, should be accounted for. This space radiation will induce many different radiation effects on spacecraft. Each subsystem or unit or component. First, there are internal or subcharging effects, so-called electrostatic discharge event due to space environment. Also, there are cumulative radiation effects, such as total ionizing dose and displacement damage dose. On the other hand, there is a transient effect called singularity effect, which is the main theme of this conference, I think. And in addition, space radiation can induce background noise increase in the scientific sensors and detectors, and thus affecting the signal-to-noise ratios of the measurement. And of course, humans and biological systems are also susceptible to space radiation. So different radiation environment and different particle species will be responsible for different radiation effect. Trapped protons and electrons and solar protons are mostly important for total ionizing dose and displacement damage dose. Low energy plasma is mostly responsible for subcharging, while high energy electrons are important factor for internal charging. For single event effect evaluation, protons and heavy ions and secondary neutrons can be important. Among these, solar proton and solar heavy ions and the energetic galactic cosmic rays, GCR, and neutrons are most relevant for SEE, for deep space missions. So I will focus on this environment in my talk. Before I move on, let's go over a couple of useful concepts. We use linear energy transfer, or LET, a lot in our field. LET is the energy transfer to material per unit path length as an ionizing particle travel through it. Typically, unit MeV per centimeter or unit length. Sometimes we use mass LET, LET divided by the density of the shielding material. MeV square centimeter per gram. LET is material dependent. And on the other hand, there's a concept called non-ionizing energy loss, NIEL, which is energy transferred to material per unit path length to displaced atoms from their lattice site. NIEL also material dependent, and the units are same as LET. So LET can be used to compute the total ionizing dose. On the other hand, the NIEL are typically used to compute displacement damage dose. So another way to look at the NIEL and LET, total ionizing dose, and DDD, displacement damage dose, is that material radiation going through material, it will lose energy. Total energy loss will be summation of the energy loss to ionization and energy loss to displacement. So ionization related to LET and displacement related to NIEL. As I mentioned, they can be used to compute total ionizing dose and displacement damage dose if you know the environment. On the other hand, in my kind of analogy, for single event effect, the SEE is a special case of ionizing dose where even a single particle can generate a lot of electron hole pairs. There is ionization sufficient to change device properties. Typically particles with high LET values. This is just for your information. Between LET and IEL, relative energy disposition between ionization and displacement, this figure clearly shows that most of the energy loss will be spent on ionization. The LET typically 3 orders of magnitude higher than the NIEL, which means that the ionization is dominant radiation effect when you have a charged particle environment. So coming back to SEE, this is a graphical illustration of the SEE phenomenon. Single heavy ion can generate sufficient electron hole pairs, while protons typically require nuclear reactions to produce secondary heavy ions, which are subsequently responsible for SEE, single event effect. However, these days, for very sensitive devices, direct ionization by protons can also induce SEEs. The end result of this SEE phenomena is to cause charge to be injected in sensitive area, sensitive volume in device, and to generate pulse of erroneous signal propagating in the circuit, causing some errors in the device. There are multiple different types of SEE. Typically, we divide into soft error and hard error. Soft error or recoverable SEE include single event of upset SEU, single event functional interrupt SFE, and single event transient SET, and among other soft errors. At the same time, there are other types of non-recoverable SEE, hard errors, single event latch-up, SEL, single event burnout, single event gate rupture. So there are whole different kind of SEE phenomena that device people has to consider. I'm not going to go over detail of each phenomena because all of you audience are very familiar with the SEE event. So let's get back to the environment responsible for the single event effect. Since the radiation environment in our solar system is actually strongly influenced by the sun's activity, which is termed solar cycle, I'd like to start with a brief introduction of the solar cycle. As you know, the sun is not static, it's very dynamic, as you might guess, and solar activity level ebbs and flows. So typical solar cycle include about 4-year buildup in solar magnetic activity, and followed by about 7-year decline in solar magnetic activity. So typically we consider solar cycle to be 11-year solar cycle, although there is no kind of distinct, clear boundary of the solar cycle. But during the 11 years of solar cycle, we typically have 7-year solar max when the solar activity is higher, and 4-year solar mean when the sun's activity is relatively low. So 11-year solar cycle is a typical solar cycle we are considering. So how do we know or how do we determine the level of sun's activity? We use the sunspot numbers. The sunspots are sites of very intense magnetic field in the sun's photosphere, the visible surface of the sun. They last from 1 or 2 days to several weeks. And sunspots usually come in pairs of opposite polarity, north and south. The fact is that the field, the magnetic field at the sunspot is so strong in the central dark portion that actually the strong magnetic field suppresses heat transfer. That's why the sunspot it appears darker than the photosphere, even though the magnetic activity is much higher than surrounding area. And sunspots actually are about 2,000 degrees cooler than the surrounding photosphere and can be up to 50,000 kilometers in diameter. And sunspots are mostly responsible for solar flares and coronal mass ejections, the two primary sources of solar output. They are closely related to the sunspot magnetic disturbance. So this chart shows the solar cycle dating back to 1970s, covering solar cycle 21, 22, up to 25. Right now in 2023, we are in solar cycle 25. As you can see, we are at the increasing phase of solar cycle, which will be peaked in 2024 and 2025. As you can notice also from this plot, is the last solar cycle 24, was historically low activity. So it has some implication for the GCR environment, like I'm going to explain a little bit later in my presentation. So we are in solar cycle 25 at this time. So let's talk about SEP, the solar energetic particles. Speaking of solar energetic particles, there are two phenomena from the sun that are responsible for SEP. One is called solar flare, which is thought to be the only physical phenomena responsible for SAP until as late as early 1980s. These days, now is a general knowledge that both solar flares and coronal mass ejections are the cause of the solar particle event. Solar flare is impulsive and happens in a very small region, and while CME, coronal mass ejection, is more gradual, it happens in a wider spatial scale. They are distinguished by the source of particle acceleration. Again, solar flare, it's a very short, narrow region, kind of a jet-like phenomena. As coronal mass ejection is kind of a wide phenomena accompanied by the CME shocks, covering wider spatial scales. So both solar flares and CME are responsible for solar energy particle event. So this is two examples of recent solar flare and CME to illustrate the main difference. Left is solar flare. As you can see, there's a kind of explosion, very short explosion, and to the bottom right portion of the movie. And the right is this coronal mass ejection. As you can see, it's coronal mass ejection spatial scale is much larger than this and the solar flare. Also, time scale is much gradual than solar flare. And solar coronal mass ejection is responsible for the most powerful SEP in the solar system. This happens in January 23 of this year, solar coronal mass ejection, and solar flare, which happened in the last March. So it's kind of happening real time these days. So speaking of solar energy particle event or solar proton event, solar particle event, all kind of synonymous. They are all periodic and sudden increase in medium energy tends to few hundred MeV charged particles. SEPs are accelerated near the sun and rapidly move out along the solar interplanetary magnetic field, so-called Parker spiral. As you can see here, sun's rotating. So sun's rotating means that particle coming out from the sun follows some kind of a garden hose spiral motion. So to your right, the right figure kind of illustrates how the particle from the sun reaching the Earth. So because of the Parker spiral, we call Parker spiral motion, the particle from the west limb of the sun actually we see from the Earth because of the Parker spiral. So particle from the sun, solar energy particles, they are followed by the spiral motion in the interplanetary space. And there are a lot of other particles in the solar particle event, but protons are the dominant component. That's why we also call solar proton event. Up to 10% can be helium, and 1% can be all other elements, up to ions, and uraniums. And event by event, we have a different characteristics I'm going to show later. And SEP is a high intensity event with a flux with order of magnitude above the GCR background. So we can call the SEP is cosmic thunderstorm. And SEP can reach peak within tens of minutes to hours of onset and may last for two or more days. Actually, up to 2 weeks they can last. And of course, this is obvious. The probability of the event varies with the solar cycle. SEP probability is higher at solar maximum, is lower at solar minimum. But during the solar minimum, it doesn't mean that SEP cannot happen. It can also happen, but the frequency and probability of SEP having SEP during solar minimum is low. Okay, so SEP event can be characterized by the peak flux during the event, a total fluence of the event, and spectral hardness, the time to peak, time to decay. Or there are many different features, parameters we can define the solar particle event. As you can see from the figure in the bottom left, each event can have a different characteristics in terms of the duration and spectral shape. So we use, as I'm going to show later, but we use some kind of a statistical model to estimate this radiation environment for a mission. So because we cannot predict the solar particle event with a high accuracy for their characteristics. So this is kind of a solar particle event summary. I'm going to go over the galactic cosmic ray and GCR. And GCR, actually, it was discovered by early 1900 by Victor Hess from the balloon experiment. Hess detected elevated ionizing radiation at high altitude, which he attributed to cosmic source. As you can see, as you go up higher, and up to 20 kilometer altitude, radiation environment becomes increasing up to 20 kilometer altitude and decrease. So as you go up, and the radiation environment becomes higher, and Victor Hess attributed this phenomena due to galactic cosmic ray from the outer space. GCR, they are all relativistic ions originating from outside the solar system, arriving steadily from all directions. So it's omnidirectional. Compared to SEP event, which is sporadic and very unpredictable, GCR environment has been stable within 30% over 10,000 years, or more than 100,000 years, and stable within a factor of 2 over 1 billion years. So they are very stable environment compared to the SEP environment, which is really unpredictable and sporadic. And you can find all elements up to uranium ion in the periodic table, found in the periodic table, as you can see here. And the figure shows the kind of relative abundance of the GCR ions. We found typically, and most atomic nuclei strip of electrons. So they all typically 99% of the GCR are fully stripped, so fully ionized. About 90% of hydrogen and 10% of helium and heavy element. And of course, we do have electron, antimatter, and other particles, but mostly hydrogen and helium are comprised of the GCR environment. Of course, elemental isotopic composition is determined by the source, nuclear synthesis in the supernova and so on, and process that occurs during the propagation, spiration, and decay. in the interstellar region. As I mentioned, they are mostly fully ionized, and they are all proton-bearer nuclei of the heavier element. Energy can be very high, up to GeV, also sometimes tera-electron volt. If you remember, solar particle event, the protons and heavy ions from solar particle event, they typically go up to a few hundred MeV. But GCR, compared to SAP, energy of the GCR can be very high. You're going up to GeV range. Now again, it's coming from all directions, found everywhere in the interplanetary space. Actually, cyclic variation is solar cycle. As I mentioned, on the environment, space environment in the solar system is strongly influenced by sun's activity. But in this case, the GCR environment actually lower in solar max, in higher solar mean. This shows the solar modulation, the GCR environment for protons and heliums and oxygens and ions. At 1 AU, it shows the variation of the environment for different solar activity. As you can see, the solar modulation is more pronounced in lower energy regions. The anti-correlation is due to the fact that during solar max period, when the sun is very active, sun's magnetic field is stronger than during the solar mean period. This means that GCR environment, the GCR particles coming from the outside of solar system will have more stronger barrier, for example, barrier bumper, to come into the solar system during solar max. So GCR flux is lower during solar max, vice versa during solar mean. So this is something we need to understand. Okay, and of course they're all charged particles, so they are governed by the magnetic field, and trajectory will be bent by interplanetary magnetic field. Okay, so this figure clearly illustrates the correlation or anti-correlation between the sun's activity and solar and GCR flux level. The figure in the top is the greater than 10 MeV, greater than 30 MeV proton fluxes as a function of time. And the second plot is the representation of the heavy ions, heavy ion environment. As can be seen from these figures, it is apparent, it is obvious that solar particles are enhanced during the solar max period, which you can see here. And while GCR environment are higher during solar mean here. This is another illustration of the GCR environment being anti-correlated with the solar cycle, which is represented by sunspot number as well as solar modulation potential. And the bottom is the ground level neutron count, which is a proxy of the ambient GCR environment. So it clearly shows that the GCR environment is anti-correlated with the sun's activity, solar potentials. Okay, let's see. So summary, comparing the SPE environment, SEP environment, and GCR environment. So SPE, solar particle event, SEP, solar energetic particle event. They are occasional and infrequent event, typically occurring mostly during the solar cycle maximum. As I mentioned, the solar cycle, we have solar cycle typically last 11-year cycles. It's a high flux, but relatively low energy, few hundred MeV each, and only for brief hours to days period. And as I mentioned, it's mostly protons. On the other hand, GCR, they occur all day, every day. It's kind of an all day everyday background environment in the space. They varies in flux with the solar cycle. As I just mentioned, GCR level is lower during the solar max. The flux is low, but much higher energy. And also at the same time, protons and alphas dominate. But as I mentioned, all elements and the periodic table can be found in GCR environment. So how do we define the environment for space missions? We use the empirical models. So as for the GCR and the solar particle model currently available and widely used, here's just summary. Many SCP models available, which has been developed typically using the historical solar proton event database. We have a JPL model, ESP, emission of a solar particle model, and Sapphire model from ESA, and etc. They typically provide statistical estimate of the solar proton fluence or flux for a given mission duration. For example, the figure in the left illustrates the model output comparison from several models for a 7-year mission at 1 AU at 90th percentile confidence level. On the other hand, as I mentioned, GCR environment is relatively well understood, and GCR models are rather stable. The widely used model include CREAM 96 and Bardwell-O'Neill model 2020. They are kind of two top models being used in the NASA and other aerospace industry. And I like to note that actually Voyager data, which now exploring outside of the solar system, they are in the interstellar region. The Voyager data, they are being used to extend the Bardwell-O'Neill model 2020 to greater than 1 AU environment. So that's for your information. One of the problems that SEE engineering community should be aware is that, as you all know, CREAM 96 is the most commonly used tool for SEE rate calculation, which is actually based on environment in 1977. So GCR background environment used in CREAM 96 based on 1977 solar mean environment. However, as I showed a few slides back, the most recent solar minimum, including some historical low solar cycle 24, raises some kind of concern about the elevated GCR flux during the future solar minimum period. Although peak flux are relatively stable, they're not varying each other. Maybe they stay within 30% each other, but GCR background in the most recent solar cycle, solar minimum period was higher than 1977. So we may have to consider revising peak GCR flux environment to evaluate SEE rate in the future to 2009 or 2020 due to the recent trend from the 1977 GCR environment. That's something we, as a community, we need to think about for the future. Since we are talking about the mission to the moon, Artemis mission, Artemis project, I'd like to talk about a little bit about the moon environment. Actually, the moon is an interesting target for space physics. There's no significant atmosphere at the moon and no global magnetic field at the moon. And for an orbiting spacecraft, such as Gateway, the environment is dependent on relative position between the moon and the Earth and the sun. For Gateway, for example, it will spend about 73% of the time in the solar wind region and 14% of the time in the magnetosheath, and the rest of the time within the magnetotail, where the plasma sheet interaction and magnetic reconnection phenomena is a very interesting scientific topic to be explored by the Gateway. I'm not going to go over detail for this community, but this will be very interesting scientific investigation to be done by Gateway around the moon area. So no atmosphere and global magnetic field means that SP and GCR environment at this lunar surface will not be modified other than the geometric shielding effect by the moon itself. At the same time, even though the moon is very close to the Earth, and there is a lot of missions went to the moon. We really don't have a lot of measurement, actual measurement from the moon, especially for albedo neutrons from the surface of the moon. So we mostly relied on the modeling and simulation. We kind of raise a question about the effect, contribution of the albedo neutrons to the SEE for future missions to the lunar surface. So it's kind of a question mark that we have to think about. Eventually, we will be venturing into the Mars. At the Mars surface, kind of a similar physical mechanism, similar to the moon, will be happening, but we should include effect of atmosphere. And for the Mars surface environment, actually MSR-RAD, radiation assessment detector, helping us a lot in terms of the understanding of the radiation environment at the Martian surface. Greater than one solar cycle since its landing in 2012, more than 10 years ago. So MSR-RAD has provided nearly continuous monitoring of the surface dose rate, as well as spectral information for neutrons and ions in some restricted energy band over the years. So combination of the measurement by MSR-RAD instrument and the validated the radiation transport tool model assessment has led to a reasonable understanding of the Martian surface radiation environment, more than lunar radiation environment. So we have a kind of better position, better understanding of the lunar surface environment thanks to MSR-RAD instrument measurement over the last more than 10 years. So this kind of summarizes the current state-of-the-art understanding of the space environment, SEP environment, GCR environment, and surface environment at the moon and Mars are related to the SEE environment. So let's talk about briefly what kind of gaps and the future need exist to better understand, better serve the community, to better serve the radiation environment and radiation effect community for the future Artemis project. So before we get into the detail, I'd like to note that some of the material that I'm going to show next are partially from the recent study report by NASA's Engineering Safety Center, NESC study titled Safe Human Expeditions Beyond Low Earth Orbit. That is, I'm going to present some of the findings from the report on space weather and space environment that will impact human and robotic exploration in general, and radiation monitoring in particular for the future mission to Moon and the Mars. So first, related to the solar particle environment, the recent study, one of my group members at JPL, we published in paper in 2023, a recent paper in Space Weather Journal. It indicated that even with the same underlying data set, different mathematical formulation used in each model, different model use a different formulation, different statistical formulation. They could result in factor of 2 to 3 differences in the model output. As you can see in the right figure, they are same data set, but different formulation resulted in different output, factor of 2 to 4. That has the big implication for spacecraft design. This kind of implies that we as a community will need to come up with a common and unified mathematical approach to estimate the emission flows from SAP. And there's something I'm currently pushing as an activity for the community. And other findings from the NESC study that the capability to nowcast monitoring SCP event it's kind of sufficient to support crew warnings for onset of radiation event in time to implement radiation mitigation strategies. So the crews, the astronaut, they can have enough time to hide or to build some kind of an ad hoc shielding around them to be able to protect themselves from the SCP event. We do have an outcast capability to give them warnings about the SCP event. But this is very typical research topics. The capability to predict to onset of a solar energy particle event in advance is very, very limited. This is very strong, a very intense scientific research topics in these days for the community. So as for the GCR environment, the NESA studies noticed that actually compared to the SCP environment, which is very unpredictable, GCR environment has been very stable over a very long time. So GCR models that we use are sufficiently advanced that they can be reliable within 15%, plus or minus 15%, to specify proton and heavy ion flux environment that is important to crew health and single event effect. However, the main problem is the ability to predict the future GCR environment is actually limited by our capability to predict future solar cycle. As I mentioned earlier, we do have an 11-year solar cycle. And as I mentioned, the solar cycle is not really clear-cut 11-year solar cycle. It's not really clear boundary. Some cycles can last 12 years, some cycles can last 10 years. So future solar cycle, which related to future GCR environment, it's very, very dependent on the solar cycle duration. So the future GCR environment prediction is very difficult and very dependent on our ability to predict the future solar cycles. In terms of lunar and Mars surface radiation environment, we want to have more in situ measurement for the secondary neutron environment on the lunar surface, actually extending the beyond 10 to 100 MeV to GeV energies to support those and as single event effect estimate for long-term lunar exploration. At the same time, plasma environment, this is not really related to SEE environment, but plasma environment near lunar surface need to be better understood. For example, in the magnetic tail, so it's for the plasma dust interaction. This is dust in the lunar surface, the big problem for future exploration on the lunar surface. And at the same time, going to the Mars, even though MSL-RAD has been providing valuable data for more than 10 years, we need more data from other locations. As you can see, as you can imagine, MSL-RAD has been there, one location for more than 10 years. It doesn't venture into different locations because of the limitation of the driving range. So we do need to have the surface radiation environment measurement from other locations from Mars. And all in all, I think for either for lunar environment and Mars environment, modeling and simulation will still play a key role in defining the surface radiation environment at the Moon and Mars, because however we try, the limitation, the measurement, the actual measurement we can do will be limited. So modeling and simulation will be very important for the future missions. So this is about the space weather monitoring, so I'm not going to over detail. So one of the key major recommendation from the NESC study is that we may need the mission to so-called the mission to Lagrangian point L4 and L5 to produce some kind of a capability to forecast, give more warnings to the future human exploration to Moon and Mars. So I'm not going to over detail for the interest of the time, but for the interest readers can take a look at, because this chart probably will be distributed to the audience. So much for the space radiation environment aspect of the future need. Of course, there are plethora of research topics that are needed for advanced device electronics. This is not my expertise area, so I'm not going to delve into detail here, but I just included here for the audience references. But there are other kind of, in addition to research that the shortcomings, the space environment area, there's a large number of areas that we need to study from the radiation effect point of view, photonics and commercial sensors are being used a lot for space missions. So radiation effect for commercial devices are very uncertain, unknown, and microprocessors and power MOSFET and so on, and radiation effect on silicon carbide and GaN, gallium nitride devices also very important future. So there are a lot of things that the people has to study and investigate in terms of this radiation effect and radiation in addition to radiation environment. So as a summary, this is just some kind of a casual summary that I'm providing, and nothing special. So next human exploration to the moon is fast approaching. Actually, we will be seeing astronauts orbiting the moon next year, hopefully. And space radiation is and will be a continuously key factor for all our missions, for science and engineering technology, and either for spacecraft and for human. And I mean, we have, space radiation discipline has been well established over the space age since 1950s. But there still are areas for new discoveries and for also improvement. For example, as I mentioned, we need to have more measurement, more data from the surface of the moon and Mars. And also radiation effect on emerging new technologies and commercial off-the-shelf part will be also important. And also, although I didn't really discuss in my talk, and there's always a big uncertainty related to the radiation effect on biological system, humans and cells and biological system, both acute and chronic. And so there's a lot of things to be done, to be improved, and there's a lot of challenges for the future missions from the both environment aspect and device aspect. With that, I'd like to conclude my talk. Thank you for your attention.